Hey guys, in this video we are going to talk about approximating the area under the curve and then develop this idea of the definite integral. So if we're talking about integration, one of the reasons we want to integrate is we want to find the area under the curve between specific x values. So let's say we have this function that looks like this. I'll call this f of x, and we're looking at this between a and b. Integration will find the area under the curve. And what I mean by that is between the curve and the x-axis. So I'm talking about this shaded region right here where I'm bounded by the x-axis and the lines x equals a and x equals b. We could find that area under the curve by doing integration. But one thing we could do is we could approximate that area under the curve. And we could look at a left sum and a right sum. So what if we were to take this guy and we were to split it into intervals? If I want to look at the left sum, then I'm going to start at that left endpoint. Maybe I want to split into 4 different intervals. So my left endpoint in that first interval would be here. And then we would go over, and then we could make a rectangle. And the reason I would want to do rectangles is because I know how to find the area of a rectangle. It's going to be really easy to find that area of the rectangle. But you can see how I'm using that left endpoint to guide the creation of the rectangles. So if I were to find the area of each of those 4 rectangles and then add them up, that would give me a pretty good estimate for that area under the curve. So we would call that a left sum. So we're looking at summing up the area of each of those rectangles, and to find the area is going to be length times width. Well, all of our lengths are going to be the same, and to find that length, we're going to look at subtracting those endpoints, b minus a, and we're going to divide by how many rectangles we want to create. So let's suppose this guy was at 1 and this guy was at 2. The width of these rectangles would be 2 minus 1, and then we created 4 rectangles. So each of these would have a width of 1/4. The height of the rectangle is going to depend on that curve at that left endpoint. So the height of this rectangle is going to depend on what's happening at A. So we would find that height by plugging that x value into the function. And then the area of that rectangle would be width times height, which would be delta x times the height of the function at, in this case, A, which we could, maybe this one's at 1. And then we would move over delta x units. So in this case, if I move over, I would be at 1/4. So now I'm looking at the second rectangle, which is going to have a height of f of x plus 1. In this case, it would be f of 1/4 times that width of delta x, and so on. I would do that for every rectangle. If I'm looking at the right sum, so I'm going to clean my picture up a little bit. Let me see if I can do that. The right sum is going to look at the right endpoints of the graph. Go back to my shaded region between A and B. So if I'm looking at this right sum, I'm using that right side to form the rectangle. You see how these rectangles are going to be a little bit different than the other rectangles that we had for that left sum. But the idea is the same. We're going to add up the area for each of those rectangles, only this time we're using the right end of the rectangle to find the height. So you can see how this is slightly different here. Instead of using the 1 in this example, I would use the 1/4. And then I would use 2/4, which is a half, then 3/4, and then 2 to find the heights of those rectangles. So then what's going to happen is we're going to find a left sum and a right sum. One of those will overestimate what's going on. One of them will underestimate what's going on. So the actual area would live between these two values. Now, if we were to increase the number of rectangles, let's say we just had, and so we did 4. Let's say we had 10 rectangles. If we had 10 rectangles, then this area would be even closer to the actual area. And we would start seeing that left sum and that right sum as we increase the number of rectangles get closer and closer together. So that's the idea that's going on behind integration. So let's look at how do we approximate these different areas. Let's say we want to find a left sum with 4 subintervals for the function 5 over 10x plus 1, and we're looking at this between 0 and 2. This L4 means I'm looking at a left sum for 4 rectangles. That's the notation we're going to use here. So we're going to draw the picture. So I'm just going to draw a quick sketch of this picture. We could pull it up in Desmos also. I'm just doing it on my calculator off to the side. 5 divided by 10, x plus 1. It's going to cross that y-axis here at 5. And it's going to look something like this. Going from 0 to 2. We're looking at 4 subintervals, so 4 rectangles. So this would be at 1. If I'm looking at how wide those rectangles are, remember it's b minus a over n. So this is going to be 2 minus 0 over 4, which is 2 over 4, or 1/2. So this would be at 1/2, 1, 1.5, and 2. Let's draw those rectangles in. So we're trying to find the area that's shaded in here. And I'm not going to actually shade that in right now because I want you to be able to see my rectangles. Left rectangles means I'm using the left endpoint. So in that first interval is between 0 and 1/2. Here's my rectangle. Second interval. Third. And then fourth. So you can see how this is going to overestimate the area because these rectangles are a little bit bigger than what that region is looking like for each of those 4 subintervals there. So let's find that left sum. L4, I'm going to find the area of each rectangle. So that first one, the base is a 1/2 a unit wide. And to find the height, I'm going to figure out what the function value is at 0. That's the left endpoint in that first interval. So that's going to take care of that first rectangle here. And then we're going to do the same thing for the second rectangle. It's going to be 1/2 f of the left endpoint. The left endpoint is at 1/2, 0.5 plus, so that's that one. The height is 1/2. That left endpoint is at 1, which takes care of that third one, plus 1/2. And that left endpoint is at 1.5. So now we're going to plug those numbers into the function to figure out what that height is here, 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 and here. So if I plug 0 in, I'm going to get a 5. If I plug in 0.5 here, I'm just going to do this in my calculator. 5 divided by 10 times 0.5 plus 1. I'm going to get a decimal, about 0.83333. I'm going to use 4 decimal places so I get a really good final answer. When I plug in 1, I'm going to have 5 over 10 times 1 plus 1, with 5 over 11, which is about 0.4545. And when I plug in 1.5 in here, I got 0.3125. So if I were to add all that up, I would get about 3.3002. Now this guy, like we said, is going to overestimate the area. So now let's look at the right sum. Same kind of concept. I'm going to redraw my picture here. Same picture. Graph crosses the y-axis at 5. I'm still looking at what's going on between 0 and 2. This is still at 1. This is still at 1/2. And then 1.5. I'm still looking at this. But now when I create my rectangles, I'm using a right sum for 4 rectangles, is what that notation means. So when I draw my picture, I'm using the right end of each interval. So this first interval goes from 0 to 0.5. So there's my rectangle. That second interval goes between 0.5 and 1. So I'm going to go up to 1, draw my point, go over. Same thing here. This interval, the right endpoint is at 1.5. Draw my rectangle. And then I'm at 2. Draw my rectangle. So you can see how these rectangles are going to underestimate what's going on with that area. I need to find the area for each rectangle. Again, it's base times height. That base is 1/2. The height is going to depend on the height of the function at the right endpoint. Our right endpoint is 0.5 for that first interval. So this would find the area of that first rectangle. That second one has a height over here at 1. Third one, we're going to get the height by plugging in 1.5. That's going to find this. And that last one, we're going to get the height by plugging in 2. I'm going to plug these in off screen using my calculator. When I plug in 0.5, I get about 0.8333. When I plug in 1, I get 0.4545. When I plug in 1.5, I get 0.3125. And then when I plug in 2, I'm going to get 0.2381. If I were to add everything together, I'm going to get about 0.9192. And you can see how this is going to underestimate what's going on with that. So we know the actual area has to live between these two values. Would be between 0.9192 and 3.3002. And the more rectangles we have, the closer this area would get to this area. If we were to redo this with, say, 10 rectangles, we would see that gap between those two areas get smaller and smaller. Let's look at another example. Let's find the left and sum and the right sum for the function 1 over 1 plus x from 0 to 1. So this is where you may want to take a minute, pause the video, try it, and then come back and check your answer. So if we were to look at this one, it would be nice to draw a picture of the function first. So this function, 1 over 1 plus x, if I plug in the number 0, it's going to cross at 1. I plug in 1, going to cross at 1/2. So here's 1 here. I'm going from 0 to 1. This graph looks something like this. I want to know what's going on between here. What is that area under the curve? we're looking for a left sum with 5 rectangles. That's what this notation means. So if I'm looking for a left sum with 5 rectangles, I've got to figure out how wide each rectangle is. Sorry about that, guys. I had to pause the video and resize the screen. It was not wanting to cooperate. So we're going to do b minus a over n. So these are my a and b. So 1 minus 0 over 5 because we want 5 intervals. So each of them is going to be 1/5 or 0.2 units wide. So we're going to go 0.2, 0.4, 0.6, 0.8 up to that 1.0. 0.2, 0.4, 0.6, 0.8 up to 1. I'm going to cheat. I am going to copy this picture because we're going to use it for that next one. So I'm going to draw my picture using that left endpoint for each. So my picture is going to look like this. Left endpoint, draw the rectangles, left endpoint, left endpoint. So you can see these are going to overestimate just a little bit also. So to figure that out, remember it's length times width. So that length is 0.2, and that width is going to be what's going on that left endpoint. That left endpoint for that first interval is at 0. And then we're at 0.2 for that second interval, 0.4 for the third, 0.6 for the next one, and 0.8 for that last one. We need to know what those values are, so I'm just going to plug 0, 0.2, 0.4, 0.6, 0.8 into this function. When I plug in 0, I'm going to get a 1. When I plug in 0.2, I'm going to get a 0.8333. When I plug in 0.4, I get 0.7143. And then we get 0.625. And then 0.5556. And when I add all that together, I get about 0.7456. So that would be the overestimate that's coming from that left sum. So now let's look at that right sum. Still 5 rectangles. Now we're using the right endpoint. So that first interval, here's my right. There's my dot that's on that curve, and I'm drawing my rectangle to the left. Dot on the curve left. You can see how these are just slightly below. So these are going to underestimate the area. So let's find that right sum with 5 rectangles. The width's still 0.2, but now I'm going to use that right interval for each of those rectangles. So I'm going to start with that 0.2. That would give me the height of that first rectangle. 0.4 is going to give me the height of the next one. 0.6, that third one. 0.8 is the fourth one. And 1.0 would be that last one. Now I'm going to plug in those values. So when I plug in 0.2 into my original function up here, that's going to give me the height of that rectangle. 0.8333. 0.4 is going to give me 0.7143. I'm using 4 decimal places again to get a good estimate. I get 0.625 for the next one, 0.5556 for that next one, and then 0.5 for that last one. So when I add all of this together, after I multiply it out, I'm going to get about 0.6456. And we said that's going to underestimate the area. So the actual area would live somewhere between 0.6456 and 0.7456. So as far as over and underestimating the area, it's not always the case that the left overestimates and the right underestimates. Sometimes it's the other way around. It really just depends on the function and the rectangles, but it's guaranteed that one will overestimate and the other one will underestimate. So the actual area will always live between the two values. Sometimes we can find the area of the rectangle, I'm sorry, the area under the curve by using a geometric formula. We just really need to know what the graph looks like. If it's something that's easy for us to figure out, let's use geometry to help us figure it out. So these are more difficult because they are not geometric formulas. I don't have an equation that would figure out this curved area here. So two sides are these sides, the three sides are straight, but this one's curved. There's not a geometric formula for that. But what if it were a circle? Or what if it were a rectangle? Then maybe I could figure it out. What if my graph was something like this? Maybe looking at y equals x, and I'm looking at what's happening between 0 and 3. The area under the curve, and again, that means between the curve and the x-axis would be this, and that would be really easy for us to figure out the area for. So we would do that by using a geometric formula. For this case, it's a triangle. So area of a triangle is 1/2 base times height. So in this case, it would be 1/2. That base is 3. And that height, if we were to plug 3 into that equation, we would get 3. So we would end up with 9/2 or 4.5 for that area. So let's look at a few more. So let's draw a picture of what's going on. We are looking in this case at the function y equals the square root of 4 minus x squared. So let's do some fancy math here. If I square both sides and then move that x squared to the other side, this is a circle. Now, because we're looking at the positive square root, this is the top half of the circle. And they are limiting our x values between -2 and 2. So if I were to graph this circle, this is centered at 0, 0, with a radius of 2. We know it's the top half because it's the positive square root, which means positive y values. So our graph is going to look like this. So we're looking at this function between -2 and 2. The area between the curve would be this area. And that would be really easy for us to integrate, to figure that area out. This is not an easy one to integrate. That's something that we could talk about in Calc 2 using something called a trig substitution. But we could figure the area out. So to figure that area out, we're going to use the area of a circle. Area of a circle is pi r squared. I want half a circle, so I'm going to use 1/2 pi r squared. That radius is 2. So I'm going to get 1/2 pi times 4, which is going to be 2 pi. So that's the area for that shaded region. Let's look at that next one. We're integrating from 1 to 5. We need to know what this equation looks like. So I'm going to do the same thing. This is my function. Y equals the square root of 4 minus x minus 3 quantity squared. So I'm going to square both sides. I'm going to add this to the other side. Again, this guy's a circle. It is the top half because it's a positive square root there. This circle is not centered at 0, 0. It's centered at 3, 0. There's your HK. And the radius is 2. So let's draw a picture of what's going on. Circle centered at 3, 0. Radius is 2. So I'm going to draw a sketch. So from the center, I'm going to go up 2. I'm going to go left 2. And I'm going to go right 2. So here's my picture. So to find the area, again, it's 1/2 pi r squared. That radius is 2. So this is going to be 4 times 1/2 times pi, which is 2 pi. Again, that one's 2 pi. So same figure, just shifted along the axis. And then let's look at 19. We're integrating between -3 and 3. So those are your cutoffs on the x-axis. You could think about cutting this off with vertical lines there. And we're looking at 3 minus absolute value of x. So that absolute value function is shifted. If you think about transformations, it is reflected over the x-axis and shifted up 3 units. So if I were to graph this guy, normally it would look like this, but now we're going to flip it over and then shift it up 3. So it looks like that. So this is crossing at 3 and -3. We have a triangle. Every triangle is 1/2 base times height. That base is 6 units wide, and that height is 3 units. Then we have 1/2 times 6 times 3, which would be 9. So this guy would evaluate to be 9. The definite integral has a set of properties. Remember, we're talking about the area under the curve now. So if my left bound and right bound are the same, let's think about that rectangle thing again. So I'm looking at integrating a function. I'll call it f of x. Normally I think about what's happening from A to B, but if my A and my B are the same thing, if you think about that rectangle has no width, and because it has no width, then that area would end up being 0. If I change the lower and upper bound, it's going to change the sign of that value for that definite integral. If I integrate from a to b of k, where k is some number, just some constant, times f of x, I could think about pulling that k out and then integrating from a to b. The sum and difference formula still holds. So if I integrate from a to b of f of x plus or minus g of x, I could think about integrating each piece separately. And then the last property says if I'm integrating from a to b, I could split that up between 2 regions if I needed to. So I could think about a to b integrating from a to c. So this guy, and then integrate from c to b, and this guy. You can see how these would add up to that original region, a to b. So one other thing we need to talk about when we integrate something that is above the x-axis, we're going to get a positive. And we're going to get a negative if the function lives below the x-axis. So if those y values are negative, so this would give us a positive value. If our function was doing something like this, and I wanted to know what's happening between a and b, I'll call this function g of x. See how that function between those values live below the axis? Then now I'm going to end up getting a negative number. So that negative just means it lives below, whereas positive means it lives above. Sometimes when you integrate functions, you could have functions that live in both places. Maybe I'm integrating this function between here and here for whatever reason. This guy would end up being a positive area, this would end up being a negative area, and this guy would end up being a positive area. So you could think about it in three pieces, and you would end up getting different signs. And then the actual area between A and B would be the sum of all of those. So let's look at how we can use those properties to figure out some things. So suppose that f of x between 0 and 4 has a value of 5, between 0 and 2 has a value of negative 3, and g of x between 0 and 4 has a value of negative 1, and the integral from 0 to 2 of g of x is 2. Let's look at 29. We could think about splitting this up as integrating from 0 to 4 of f plus 0 to 4 of g. And then I know each of those. 0 to 4 of f is 5. And 0 to 4 of g is negative 1. So I'm going to get a value of 4 for that one. So you see how we're using the properties to help us out there. 30. I'm going from 2 to 4 of f plus g. So I'm going to think about integrating 2 to 4 of f plus 2 to 4 of g. So let's think about what we know. We know that 0 to 4 of f is 5 and 0 to 2. So I don't know what f looks like. Maybe it looks something like this. So maybe this is, here's my axis. Ignore that one. So 0 to 2, because it's negative, right? This would be a value of negative 3. But 0 to 4, this whole shebang here, should end up being 5. So then we can figure out what 2 to 4 for f would be. If this whole thing has to be 5, and this piece is negative 3, then that missing piece has to be 8. Let's do the same thing for g, because we're going to need that. So for g, they're telling us from 0 to 2 is going to be a positive 1. And again, I don't know what this function looks like, so I'm just kind of creating something here. So from 0 to 2, this has a value of 1. Oh, hold on a minute, it's 2. 0 to 2, this has a value of 2. But the whole thing from 0 to 4 would have a value of -1. We know these two areas together have to add up to that. So 2 plus something has to equal -1. So that something has to equal -3. So now I think we have all the pieces to solve all these problems. So we know this piece is going to be 8. This piece is going to be -3. So our answer is going to be 5 for that one. Let's do one more of these. Let's look at this one. So we could think about splitting this up and then pulling that constant out for each of these. So this is equivalent to this. That's a 2. So 3 times the integral from 0 to 2 of f of x minus 4 times the integral from 0 to 2 of g of x. We know this piece is a -3. And we know this piece is a +2. So we get -9 minus 8, which is -17 for that. So you can see how we use the properties to help us figure those out. But what if we have a picture? Let's look at this. We'll look at just a few of these. So they're giving us the areas for each of those regions. Notice that B lives below the axis, so this is actually a negative. And notice the D was below the axis, so we're going to think about this one as a -2. They gave us the area, which would be positive, but because we're using properties, we have to think about where it lives also. So let's look at a few of these. 32 is asking us to integrate from 0 to c of f of x. So 0 to c would be just region C, which would be 10.667. 34 is asking us to go from B to D. So B to D is going to include these three areas. I know this guy is a -4.951. That's region B. C is a +10.667. And then D is a -3.584. So that total area is going to come from adding those values up. So I'm going to do that off screen. -4.951 plus 10.667 minus 3.584. I got 2.132. If we look at 36, we're going from 0 to D. So 0 to D would be these two regions. C is a positive value. And then D is a negative value because it lives below the x-axis. So we're just going to add that together. And then let's look at 38. 38 is integrating from A to D. Okay, but that's not smallest to biggest x value. We're going to have to flip that. And when I do flip those limits of integration, it changes the sign of the value. So I have to keep that negative there and be careful when I compute this. So A to D is going to include regions A, B, C, and D. A has a positive value. B has a negative value. C has a positive value. D has a negative value. A little bit more room. Let me make this a little bit smaller. So when I plugged that in my calculator, I got a negative 4.949. Let's look at 40. Again, those limits of integration are backwards, so we have to change that sign. And now we're just going from A to C. So A to C are going to be regions A, B, and C. Region A is 2 point, forget the negative, 2.817. Region B is a negative 4.951. Region C is 10.667. I ended up with a negative 8.533. And then we'll do one more. We can look at C to B here. We're going to have to flip that. It has to go from smallest to biggest. So B to C would be those two regions. That's going to be region B is negative 4.951. Region C is 10.667. I ended up with a negative 5.716. So that's how we can use the properties of integration and definite integrals to help us figure some things out.